Welcome back to the Glider Fly Project. In this video, we're going to review Newton's first law of motion and center of gravity. Again, with these series of videos that I'm introducing for reviewing theory, I will have the resources that I used on the description of the video below. As always, I encourage you to continue to learn more about these subjects. Again, I'm just going to review them and try to apply their definition and how we're going to be using them in terms of flying the gliders. So it's a quick review. So make sure you go out there and read more about them if you need to. But with that, let's start. So, what is Newton's first law of motion? Newton's first law of motion states that an object at rest remains at rest, and an object in motion continues moving at a constant velocity in a straight line unless acted on by an external force. Now, I would assume that none of you would argue with the first statement because if we look at a two-dimensional diagram of a table with a ball on top of it, I don't think anyone would argue that that ball would stay there unless someone moved it. That's pretty much what the first part of Newton's first law of motion is saying. That object will remain at rest unless something moves it. So now, if we were to give it a tap there, then by Newton's first law of motion, if this surface was slippery and there was no friction, then that ball would continue to move with a constant velocity, and the velocity is caused by that tap. And unless you prevent it from falling off the table, it would continue to go in that direction. But if we apply an equal force in the opposite direction of that which we started with, then that ball would come at rest. It would go back to being at rest, just at a different location. And now, if we wanted to move that ball down, then we would have to apply some force there to move it down. And that ball would move down unless you apply an equal and opposite force to cancel that initial reaction. Now, if I asked you, I want you to move that ball back to where it started with one force application, then you'd probably say, well, apply a force here. And I would say, you're correct. And now, if I say, okay, well, let's make sure it doesn't continue to go in that straight line and fall off the table, then you would say, well, I could apply an equal and opposite direction this way. And I would say, yes, but what if I said I don't want you to do that? I want you to apply two forces to cancel out that force. Then, if we were going to start doing that, I'd probably want to have a coordinate system. And I would say, okay, let's say left and right is in the x direction, and up and down is the y. So, what we've done so far from the very beginning to move it is apply a force in the x direction, positive, to move it to the right. Then we canceled that force by applying an equal and opposite force in the negative x direction. Then we went to apply a force in the y direction while going down, and then a force in the y direction while going up to stop it. So if we applied this force, it pretty much was some direction in the x and y. So if you look at it, if you just looked at the motion of the ball, it was moving to the left. So that had to be a negative direction in the x, and it's some force I'm applying. So that's a force in the x direction to the left, indicated by the negative. Then it's moving up. So it has to be a force being applied in the positive direction of the y-axis. So that gives you a hint of what directions and what amount of force you need to apply when the ball reaches back to the starting point, because you need to apply them in the opposite direction. So that just says you're going to have to apply some force in the x direction, positive, and some negative force in the y direction. But again, these forces should be equal to those that we started with to result in that force that I didn't let you apply in the beginning. So again, you're applying some force in the X, similar to how we got it to start moving in the first part, and some force in the downwards direction to pretty much stop the ball. And again, those two could be represented as a resultant force indicated by F that would have just been that initial force that I did not let you apply. So now that is in 2 dimensions, but again, that's great for cars. They move forward, back, left, and right, or in this case, the ball moving across the table. But a glider also goes up and down. That's 3 dimensions. So let's look at this, but now in 3 dimensions. So in 3 dimensions, instead of a table, we're still looking at the table, but a table in a real world, it's pretty much inside some cube, let's say. So we have a 3 dimensional box here now instead of a tabletop. And we still have the ball, and the ball is floating right now somewhere inside the box, let's say here. So looking at it from the top, it would still look like a two-dimensional problem where we're saying this was X and this was Y. But now we're introducing a Z direction, a Z coordinate. So if that ball now, if I wanted you to move it to the corner of this cube, then you'd probably say, okay, well, I'm just going to apply a force here. It's going to move in that same direction. And then before it leaves the cube, I will apply a force in the opposite direction of equal amounts of force. And I said, okay, well, I want you to describe it as 3 forces. Then you would have to break down the motions in each axis, in the X, Y, and Z. And you'd probably say, okay, well, I would have to apply a force going this way in the X, positive, then going backwards in the Y, and then up in the Z. And I would say that's correct. And, you might be, whoa, 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 but you told me I need to kind of understand based on Newton's first law of motion that ball will, yes, move to the left, but if I don't cancel that before I move it in the y direction, it's not going to move in that straight line. So you're going to have to apply some force here, again, equal and opposite over here, and same thing on the top here to stop it. And I said, yeah, you got it, because this force is a force in 3 axes. Now, we're breaking it down because, again, a plane flies in 3 directions. The glider's going to glide in 3 axes. Well, again, it might be, it's gliding in some direction, but we're going to be describing it in 3 components in the X, Y, and Z. So that's why I want you to understand, again, any motion, be it a ball floating in space, could be represented as 3 individual components in the X, Y, and Z. It's very simple, but it could be confusing if you're breaking it down for the first time as 3 separate things. Because again, no one really thinks, well, if all you want to do is move the ball here and here, why would I apply 3 different forces to it? That just seems like a waste of time. And I would say, yes, I agree. Just apply one tab and it's going to move over here and tap it right before it leaves so it stops. Versus doing these 3 force tabs where you're going to have to pretty much do it 6 times total because you're going to have to cancel each one. You're applying 3 and then applying 3 to stop them. I get it. It's kind of, you know, like overdoing it. But when you're talking about flight test and applying forces and how a vehicle moves, we want to break it down into every single component to understand how that plane is actually moving, what's the performance of it. That's why we're looking at it in 3 dimensions and breaking down the reactions of forces in 3 dimensions. Now, the next thing that we are going to talk about is the center of gravity. And NASA defines the center of gravity as the average location of weight of an object. So that just means that any object if it's a piece of paper and it's this perfect square, then the average location of that paper's weight is the center of gravity. And you could probably assume that it's probably a dead center. And I would say, yeah, you're correct. Or if you had a pencil and you try to balance it with your finger, you probably discover it's somewhere in the middle. And I would say, you're correct. Again, in these cases, because it's a simple sheet of paper and a simple piece of pencil that's just made out of wood with lead in the center, the center of gravity is where the center of the geometry is. But that's not the case if this pencil was made of half wood and let's say the other half some metal. Then the center of gravity of this object would probably be somewhere over here. It wouldn't actually be at the center of the geometry. So the easiest way to find the center of gravity for any object, especially if it's not of the exact same material, is try to balance it, because that will give you an idea of where that center of gravity might be. Now, what does center of gravity have to do with the gliders and with Newton's first law of motion? Or I'm about to tell you. So, again, going back to our handy pencil, and now that we understand that that center of gravity is somewhere in the center there, look at what we did. We went from a ball moving around to now this ball, but in a fixed rectangle shape. Now, if I wanted to move this up and down, then you would have to apply some force to make it go up. But where do you apply that force? Because if you apply it at the tip, is it going to move straight up? If you have a pencil in front of you, not one of those roly pencils, but I mean like an actual number 2 pencil, a wooden pencil, you'll realize that as you try to push it from the tip, it's going to rotate. It's not actually going to roll. It's not going to push the pencil straight. It's literally going to rotate clockwise. It's going to make the pencil start rotating. And why is that? Well, it's because you're applying a force in the direction that the center of gravity is not located. So if you were to actually apply the force where the center of gravity is, here, then that pencil would actually move up and down. It wouldn't rotate at all. Now, if you wanted to move it left and right, if you found a way to apply it on the edge of, let's say, the eraser, like if we here's the eraser part of it, which is very difficult, but you could try. Is it going to move or is it going to rotate? You'll realize if you do it pretty well that it's actually rotating. It's trying to like avoiding your fingertip as you're trying to press it. And that's because, again, you're applying a force that is not in the direction of a straight line where the center of gravity is, because the center of gravity is where that average weight is. So it's going to move with it without like rotating. And it's a very important thing to understand, because what the pencil and the center of gravity is pretty much telling you is, if you consider that coordinate system, but now instead of being a ball on a table and the table has the fixed coordinate system, if the coordinate system is fixed at the center of gravity, you'll quickly realize that that's the directions where if you were to apply a force, the object would move in a straight line. So if you move it applying a force here, it would move up. If you apply a force here, it would go left. And if you do it on the opposite side, right, again, you're applying a force on the axis that goes through the center of gravity. That will allow that object to continue to move in that velocity, in that direction, straight until something else acts on it. Now, the moment that you apply a force off of its axis of gravity, in the X and Y in this case, then it's going to start creating additional rotations, and that's because you're applying a force now that is away from where the center of gravity is. And I'm not going to cover that equation of rotation right now, but again, there is a physical equation that basically tells you how much it would rotate by in terms of like a force of rotation, like a torque, based on where you apply that force in that direction and how far away that force is from the center of gravity. And you would break it down in each coordinates, again, in the x, y, and z. Because again, here you have some length and some force you're applying, and that would actually create a rotation. So, with that said, if for some reason you wanted to apply or you couldn't apply the force in the center to move it up and down, can you apply it at two different locations to cancel the rotations and just make it move up and down? The short answer is yes. If you were to apply a force here and here, the rotations caused by them, if those forces are equally and opposite in the amount of force and also in the distance from the center of gravity, those would cancel out. So then your object would just move up and down. But again, if you could do the exact same thing by applying a force in the center, then you would just do that. It's the simplest thing to do. With that said, I'm going to stop here in terms of we've covered center of gravity and the first law of motion, Newton's first law of motion. And in the next video, I'm going to relate it more towards flight test and specifically looking at, well, where's the center of gravity in a glider? And then taking into account the surfaces on a glider, how those surfaces being away from the center of gravity allow you to be able to pitch the aircraft up or down, roll it left and right, or yaw it to one side or the other. Because again, we're pretty much trying to understand how an aircraft maneuvers, but using the laws of physics to understand again why is it actually doing that? Why is the rudder all the way in the back, and how is that helping it yaw? So again, this is a quick review. It's only about like 15 minutes. If you would like to learn more about center of gravity or, first law of Newton's first law of motion, use the sources that I provided. But again, you could go out there and look at other articles, other reliable resources to learn more about it. So until next time, continue learning and we'll see you in the next video.